but also you can find the information in the Laura Bassi Series webpage. Before to start today's seminars, and to give time for the colleague to join us, I give way to a short video about the Laura Bassi life.
Laura was born on 29 of October 1711 in Laura was born on 29 of October 1711. In 1732, she earned the degree of Doctor in Philosophy from the University, that is, of Natural Philosophy. In the following years, the young woman continued to study. In 1738, she married Giuseppe Verratti, a doctor in medicine who shared with his wife a keen interest in the study of nature. In 1745, Pope Benedict XIII admitted Laura Bassi among the elite group of scholars named Benedictine academics, but only as a supernumerary and not without resistance. Filling this role, she had to present at least one original dissertation a year. In this way, Laura played an active role inside the Bolognese scientific community. For performing her talks, Laura carried out several experiments with her husband in her own home, in a special laboratory that the couple had equipped with the most advanced tools and machines of the time. This laboratory was used not only for her personal research, but also for the private lessons in experimental physics that Laura Bassi held for philosophy and medical students of the university. The almost 30 years of high-level lessons held by Laura at her home earned her the assignment of the position, this time effective, of Professor of Experimental Physics in the Institute of Sciences in 1776. Only 2 years later, on the morning of February 20, 1778, Laura Bassi died suddenly, after having participated in a session of the Academy of Sciences the previous evening. This woman, a forerunner of female emancipation, remains an admirable example for all women of science still today.
Okay, this is already 14:35. So today's speaker is Mirjana Pović. She is assistant professor in the Ethiopian Space Science and Technology Institute, associate researcher at the Instituto de Astrofísica Andalucía in Spain, and honorary lecturer in the Mbarara University of Science and Technology in Uganda. She obtained her PhD in astrophysics in 2010 in the Instituto de Astrofísica de Canarias, also in Spain, and her main research interests are galaxy formation and evolution, in particular nuclear activity in galaxies, star formation, morphological classification of galaxies, and galaxy clusters. Mirjana has also worked over more than 10 years on development in astronomy, science, and education in different parts of Africa. Just for this, she has received several recognition and prizes. For example, the inaugural Nature Research Award for Inspiring Science in 2018, 2 recognitions from the Ethiopian Space Science and Technology Institute in 2019 and 2020. She is one science ambassador from the Science Fund of the Republic of Serbia since 2019, And this year, she has just won the inaugural Jocelyn Bell Barnard Inspiration Medal by the European Astronomical Society. Okay, if you have, at the end of the seminar, if you have some question, please raise your hands or write in the chat. But without any further delay, I pass the baton to Mirjana. Mirjana, please.
Yes, thank you, Nancy. Let me try to share my screen. Okay, can you? Okay, can you see the full screen? Okay, perfect. So thank you very much, Nancy. Before I start, I would really like to give my thanks to all organizers of this colloquium and for starting it and for giving more visibility for women in science. And I would also like to give my thanks to Sarah for inviting me to give this talk. So good afternoon, everybody, once again, and I will speak about green belly galaxies and the role that AGN might have in galaxy evolution in relation to the green belly galaxies. So during this talk, I will summarize few of the projects that we are working on in collaboration with with few African countries. And first I will go, I don't know how diverse the community is of the participants. So I will first start with just introducing the green belly and then also the B-model distribution that we have in galaxies. So basically in all big surveys that we have, both at lower, higher redshift, it's been observed that the distribution of galaxies in optical ultraviolet is B-model when we compare different properties such as colors, stellar masses, intrinsic brightness, or star formation rate of galaxies. So basically here, what I mean by this can be shown here on the right plot. I hope you can see my cursor as I move. Can you?
Yes, perfectly.
Okay, that's good, because I will be using it during the talk. So here on the right, we can see one of the figures, one of the results from 2014, one of the first results using the large sample of Sloan galaxies and including morphological information as well. And you can see that when we reproduce the color, stellar mass, we have galaxies distributed into two principally regions. One is what we call the red sequence, being mainly populated by early type galaxies, as you can see, and another one is blue cloud, being mainly populated by late type galaxies. We also do find about 30 up to 30% of late type galaxies that are in the red sequence. Either due to the very strong extinction or edge-on galaxies or due to their disturbed morphologies. And then in case of the blue cloud, we also have a certain fraction of early type galaxies. So in between these two regions is the area that is less populated by galaxies, at least when we observe in optical. And this is the area that is called the green belly, and it's been suggested to be really important one for understanding the galaxy evolution and how the galaxies are moving from being late type to early typed, or from the blue cloud to the red sequence. So basically, this is at redshift, at the low redshift, below 0.1, but this B-model distribution has been seen at higher redshift as well. So here we have the example in Alhambra survey, where several years ago we went through the morphological classification as well, using support vector machine learning, and classified all galaxies into late type, those that are in blue in these two plots, and then early type in red. And here you can see again color luminosity diagram on the left, color stellar mass diagram on the right, and again the B-model distribution when we go up to the redshift of 1. And these are a bit more recent results from 2020 using a different machine learning approach with CNN. and classifying galaxies into disk-dominated and bulge-dominated using, again, 2 surveys, SDSS at the low redshift and then candles at the higher redshift. And again, the same B-model distribution has been found at lower, higher redshift, where the bulge-dominated galaxy are basically located in the red sequence, and then disk-dominated primarily in the blue cloud. So what are some of the, just a brief summary on the properties, general properties of the Green Valley galaxies. So it's been observed in general in terms of many properties that these galaxies have intermediate values between the blue cloud red sequence galaxies. So these are just 2 examples for the stellar ages, and then the timescales, the quenching timescales versus the stellar mass. In case of the gamma survey and results from 2019, where we can see in green the Green Valley galaxies being between the 2 distributions, and then having also a bit faster e-falling times, so facing stronger change with the star formation histories in comparison with the blue cloud galaxies, but slower in comparison to the red sequence. This is another example from last year, where also has been measured beside the stellar ages. And in green, you can see, let's say, the mid Green Valley galaxies. In red and blue are also Green Valley galaxies, but those that are closer to the red sequence in red, and then blue cloud in blue lines here. And again, we can see the intermediate values of Green Valley galaxies, even when we are talking about velocity dispersion, metallicities, or extinction. In these 2 plots on the left, right, we are talking about similar samples, but the Green Valley galaxies selected using 2 different criteria. The new suggested DN 4000 break, and then the one of the color criteria. When we come to the properties of Green Valley galaxies in terms of environment, different works have been carried out, and some inconsistencies have been found as well. Going from strong relationship with environment through the mild relationship with environment, and without finding any dependence on environmental effects. This is just one of the examples where the mild trend has been seen with environment in 2020, where it's been suggested that the fraction of Green Valley galaxies in field is larger, and that this is changing, taking into account the stellar mass range. But then if we normalize that with the non-quiescent galaxies, then the effective Green Valley fraction becomes lower for the field galaxies. And again, there is a strong effect taking into account the mass as we are going toward the higher mass. When we speak about the fraction of Green Valley galaxies that has been observed in big surveys in general, and then their morphological properties, this is one of the very recent results that came out this year, and using the SDSS survey. And again, it's been the Green Valley properties have been studied in terms of the environment. So D1 on these plots are very rich environments that correspond to the filaments, and then 3 are basically field galaxies. And it's been seen in green here. You can see the Green Valley galaxies selected through the color criteria and some fittings. And it's been seen that the fraction of Green Valley galaxies is pretty much constant, so that it doesn't change with environment, and that it's below 20%. And that's a bit in line with other results, such as from Stravinsky that I mentioned previously, or the one from the AGN in 2020, where also the fraction of Green Valley galaxies have been suggested to be between 10 and 20%. But when we come to the morphological properties of Green Valley galaxies, again, depending on the study, different fractions have been suggested. In this work, for example, only about 5% of galaxies have been suggested to be early type, and about 95% spirals. while when we go to the another SDSS sample from 2014, it's about 30–70% in terms of the early type, late type galaxies. So still a lot of work is actually needed with using much larger samples, and especially when we come to the morphological properties, we are still quite limited with the classification of galaxies, even at the smaller redshift. And one of definitely difficulties in order to get more consistent results is the use of the selection criteria for Green Valley galaxies. So basically here I summarized some of the criteria that have been broadly used over the past years, including different color criteria, using both either totally optical bands or mixed between optical ultraviolet, and then the mixed between the colors with stellar mass and intrinsic brightness. Then also specific star formation rate has been used to separate between blue cloud red sequence and to select Green Valley in optical. Also correlation between specific star formation rate and color, but also star formation rate versus stellar mass. And recently, as I mentioned, the DN 4000 break. And then different fittings have been carried out as well by using different mathematical functions to fit the distribution of early type, blue type galaxies in combination with these previous criteria that I mentioned, and then using both optical and near ultraviolet data. So as we can see, quite a lot of approaches have been applied, and each of them with their limitations. This is below just an example between color criteria and then star formation rate, specific star formation rate versus stellar mass criteria using two different samples, ultraviolet and optical. So in the first work that I will present that we carried out, we actually wanted to understand a bit more different selection criteria that have been used previously for selecting Green Valley galaxies and studying Green Valley galaxies, and to understand a bit what kind of population of galaxies we are actually selecting by using one or another criteria. So what we did with Beatrice, you can see her here. She was the first MSc student in Rwanda, the first female, and this is the work that we did with Beatrice during her MSc, and now we are finalizing the paper that we hope to submit soon. And it's a project that she's now starting her PhD, being supported by the International Science Program. And the work that her MSc and then now the PhD is a collaboration between a few countries, including Rwanda, Uganda, Ethiopia, South Africa, and Spain. We are really trying to strengthen more connections and collaborations on the African continent, and then in collaboration with Europe as well. So we'll see that several of the projects that I will mention are actually going in that line. So we selected with Beatrice 6 criteria that have been broadly used using the SDSS sample up to redshift of 0.1, so that we can deal with a more complete sample. And we used both sample in optical and then near ultraviolet as well, using the GALEX data. And in optical, we used, as I said, SDSS data, and then the Max Planck catalog from DR8, where different measurements are provided, including the stellar mass and star formation rate. So the first 2 criteria were based on simply colors. On one side, the optical color, and then on the other side using the near ultraviolet and optical bands as well. And then we selected the Green Valley galaxies using, as I said, these 2 criteria, and being focused on previous works as well, where the criteria has been applied. Then other 4 criteria, another 2 have been related, are related with a specific star formation rate using now optical sample near ultraviolet, where again, here you can see the two bumps related with the red sequence and blue cloud. And then the last two criteria have been determined using star formation rate versus stellar mass, again in both optical and near ultraviolet. That again has been used broadly in previous studies. So what we did, we selected Green Valley galaxies using these 6 criteria, and then using public data, we went through the study of different properties of these Green Valley galaxies selected in different ways, including the distributions of the stellar masses, the luminosities, the star formation rates, and then studying also the morphologies and then the spectroscopic types of galaxies selected by one or another criteria. So we found that there are actually differences when we go to one criteria or another. Here is the example for stellar mass and then the absolute magnitude in R band. And you can see that when we go to the near ultraviolet sample, we are selecting a bit more massive and then brighter galaxies. When we come to the fraction of different morphological types and different spectroscopic types, here for the morphology on the left, we use the visual classification from Galaxy Zoo. So we have 3 morphological, basically 2 morphological types, the spirals and then ellipticals in blue and red. And then, as you know, in Galaxy Zoo, we still have a significant fraction of unclassified galaxies. So here we represented them as well. We did on the top is the optical sample, the optical criteria, and then on the bottom, the near ultraviolet sample and the free criteria. And we can see that especially when we come to the color criteria, we find more significant differences where when using purely optical colors, we select more spiral galaxies and less spirals, a bit more ellipticals when we are going to near ultraviolet minus optical bands. Similar has been seen when we study now the spectroscopic types. So basically for classifying galaxies into star-forming composites and then Seyfert and liners, we use the BPT diagrams and then the ratios of the emission lines measured in the Max Planck catalog that I mentioned previously. And again, we can see that smaller differences have been found in terms of the fraction of different spectroscopic types when we go to the criteria based on the specific star formation rate and then star formation versus stellar mass. However, when we come to the colors, again, a big difference has been found that basically once we add the AGN, either when we are dealing with composite galaxies or pure AGNs like in Seyfert or low luminosity AGN in liners, we basically get larger fractions in when near ultraviolet colors are used than for the optical. So these results are not surprising, but it's important that we can quantify the fraction of different populations when using one or another criteria. So basically the main findings with this very first work of Beatrice was that by using different selection criteria in different works and optical near ultraviolet samples, we are actually selecting different types of galaxies in terms of stellar mass, spectroscopic morphological types, and so on. Then the largest differences have been observed when using color criteria. So we found color criteria to be really sensitive on the type of galaxies that we are using and let's say the presence of AGN as well. However, when we go to the star formation rate versus stellar mass criteria and specific star formation rate, we found them to be more stable between optical near ultraviolet samples. And these are those that we suggest more to be used if anyhow possible. We know also that the color criteria have been broadly used and the most commonly used just because it's very easy to use them. We don't have to go through all the measurements of star formation rates, stellar mass, and so on that do require some time. Okay, so then when we come to the importance of green valley galaxies, so we can stress that these galaxies are really important for understanding all the process of star formation quenching, and then how the galaxies are moving from late type to early type, as I already mentioned at the beginning. So basically, the lower density, at least in optical, the lower density of sources has been observed in green valley than in blue cloud and red sequence, which may suggest that the transition or the time that the galaxies do spend in the green valley is much shorter than the time that the galaxies spend in the blue cloud or red sequence. But when we come to the time scales that have been measured in different works, here I just listed some of the references. Different timescales have been proposed, starting from the short timescales below 1 gigayear up to the slow quenching above 2 gigayears, and then even non-single transitions have been suggested, like in this case of in the work again of Stravinsky from 2014, where you can see now the green valley galaxies being classified into early late types, and different on the bottom plot here in the left. Different time scales have been suggested. So basically how fast the star formation rate is changing across the cosmic time. And it's been seen that the early and late type it's been suggested that early and late type green valley galaxies are actually having different time scales. Where the early type galaxies are actually going through the transition much more rapidly, like below 250 megayears, and then we can observe slower quenching for the late type galaxies. So these are suggestions that have been made in optical using Sloan. Then similar has been suggested using a different sort of analysis, including the radio data. In terms of the presence of the stellar bulge and the possibility that once we have a strong stellar bulge, we may get to the suppress of the star formation efficiency in the early type galaxies. So I here listed some of the works. And then in the recent works, also some contradiction has been found. These are two examples from 2019. In one example, we have a smaller sample of galaxies where the disk bulge decomposition has been carried out. And then the efficiency using CO data, star formation efficiency, has been measured in the two samples of galaxies, and it's been the authors didn't find any significant difference, suggesting that therefore bulges may not suppress the star formation efficiency. And this is another on the right, another example where it's been the sample has been selected where exactly the main sequence starts to bend. So basically when the galaxies start moving from the main sequence of star formation below the area, I mean to the area below the main sequence. And what the authors found is that actually the bulges in galaxies are very, very old. However, the disks are young, and they suggested the rejuvenation of these galaxies being then placed in this area of the bending or the bending of the main sequence of star formation. So in line with this, we can also mention the work from 2013 of Perez et al., where using Khalifa data, it's been, and integral field spectroscopy, it's been suggested that for the specific range of the stellar mass that you can see here, this range of the stellar mass actually corresponds to the highest growth rate in galaxies, or let's say to the shorter assembly times within the inner regions of galaxies. So when we say inner regions, we mean about less than 0.5 of the half-light radius in the galaxies. So with the GENE, we wanted to go a bit a step further and to understand a bit better what are the properties of these galaxies that we call, that have been suggested to have the highest growth rates, and that we call inside-out assembled galaxy candidates. So we, with Dežene during his MSc, we selected the galaxies from the Sloan survey and below 0.1 that do have this stellar mass range, and we went through the analysis of different parameters, trying to understand a bit better what kind of galaxies we really have in terms of their spectroscopic morphological types, but also star formation rates, and then where they are when we, in terms of the main sequence of the star formation, or in terms of on the color stellar mass diagram. And this is the work that has been done primarily in Ethiopia, but also in collaboration with Chile and Spain. And we found that significant fraction of these inside-out assembled galaxy candidates are actually composites, so that they do have AGN. So either they are composites between being star-forming AGN or AGN galaxies. So we have about 80% in total. We found that they are mainly located below the main sequence of star formation, again, about 80% of them, and also that significant fraction of them is located in the green valleys, so about 30%, and in the red sequence, about 50%. Here you can see the color stellar mass diagrams for different spectroscopic types and different morphological types that a bit show what I just summarized previously. So the main findings, we also observed where these galaxies are when used in terms of the infrared properties. So we observed the mid-infrared colors using WISE data, and then the infrared transition zone, and where in comparison with the infrared transition zone these galaxies are. So in general, the main findings in this work were that the high fraction of these inside-out assembled galaxy candidates may be in the process of quenching, and that they have a high fraction of AGN. So about 80% show the presence of AGN, which again might be suggesting that then AGN may be involved in the star formation quenching. However, we found that spiral morphology remains in place, even when we are dealing with liners at the low redshift, when we know that the majority of liners have been found to be elliptical galaxies. So in this case, the spiral morphology remains in place in general, which may suggest that the central star formation has been suppressed before actually the morphological transformation occurs. So maybe this star formation has been suppressed again in help of the AGN, the presence of AGN, but definitely we observe that it is happening before the morphological transformation occurs. So when we now go back to a bit summary of what are the suggested mechanisms responsible for the star formation quenching, we can see different possibilities that have been suggested. Going through the secular evolution, minor major mergers have been suggested as well for either enhancing or stopping star formation. The environmental effects are there as one of the suggestions for quenching star formation, the supernova winds and so on, and then the role of the AGN as well, or the AGN feedback. So this part is the one that we are interested with. And we would like to understand a bit more. So how the AGN, what is actually the role of AGN in morphological, if there is any, in morphological transformation of galaxies and the galaxy evolution. So this very first slide is now going back far away when we started having some of the largest samples of X-ray detected AGN that we know that are some of the most unbiased samples of AGN that we have. So basically, there was a series of works that came out when the XMM Chandra data started coming, and in this work that we did a long time ago, we saw that using two different surveys and X-ray detected AGN, we saw that in comparison with the optical data, these X-ray detected AGN are mainly located in the Green Valley. The same has been seen in different other works. We saw that different morphological types can be related with this X-ray detected AGN, and then both type 1 and type A AGN. When I say type 1, type 2, in this case, I refer to the X-ray type 1, type 2, not the optical classification. So basically, it's been suggested using the X-ray detection and AGN that the AGN might be related with quenching the star formation in galaxies. When going to the optical studies, the same has been suggested. These are just two examples, one using the Sloan data and Leslie's work from 2016, where the galaxies have been classified, all galaxies from DR8 version have been classified into different types, from star forming, composite, and then safer to liners. And you can see that once we start having the AGN, either in composite galaxies or more pure AGNs like in Seyfert's, galaxies start moving below the star formation, main sequence of the star formation. And a similar has been seen also using Khalifa data.
Sono Paola.
Sorry? Okay, okay, so let me continue. So the same has been seen using Khalifa data that you can see on the right, where the star formation rate has been measured now using H-alpha line, and the stellar, we have the star formation stellar mass diagram, and the measurement of the equivalent width of the H-alpha. And again, we can see that once we start having the AGN, like in liners that are all those dots that you can see in red, or those in stars that are mainly either composite or Seyfert 2, the galaxies start moving out of the main sequence of star formation. So with Antoine, we wanted to understand a bit better what are the properties of AGN and AGN in the Green Valley, and what might be the role of AGN in this morphological transformation. So what we did, it's a work that we actually started, the first part of the very first work we did during Antoine's MSc. So Antoine is the very first student to do to get his MSc in Rwanda in astronomy. Now he's doing his PhD in South Africa at SAO. And the work that we are doing is a collaboration between South Africa, Ethiopia, Rwanda, and then Spain as well. And with Antoine, we selected a sample of AGN and non-AGN galaxies in the Green Valley using the color, restrain colors. We checked the extinction as well. And we focused on the galaxies in the cosmos survey. So in average, our redshift is around 0.6, 0.7, but we have the galaxies all up to the redshift of 1. And we wanted, as I said, to understand better the properties of both AGN and AGN, measuring these properties in a consistent way. We used both optical data from the public Cosmos catalogs and archives, and then our own SALT data, and then the far infrared data from Herschel and Spitzer. So the main studies that we went through were the study of the star formation properties, the morphology, stellar populations, and then currently the properties of the oxygen free emission line. So in the first part of the work that we did, we focused on understanding the star formation properties of AGN, non-AGN. So the AGN have been selected using the X-ray data and X-ray over the optical luminosities. But then we also are talking about AGN, although selected in X-rays, that are also emitters in far infrared. So to measure star formation rates, we used infrared luminosity. So basically, we went through the SED fitting using LaFar code and using Herschel far infrared data, Spitzer 24 microns data as well. And we measured the far infrared luminosity through far infrared luminosity star formation rates. We used two different sets of templates for non-AGN and for AGN. For AGN, with the 11 templates that we used, it permitted us to measure what is the fraction of AGN and then to remove that AGN contamination so that we can measure the star formation rates being related only with the host galaxies. So what we found at the end, on the right, you can see the star formation rate stellar mass diagram, and we found a bit opposite, or let's say a different trend than when compared with optical previous optical results that I mentioned, where now for AGN we found that the majority of these galaxies are actually located on the main sequence or above the main sequence of star formation and not below the main sequence of star formation, as suggested in previous optical studies. So basically, once we do have the far infrared emission, the scenario that we are getting is different. However, we know that AGN are hosted by more massive galaxies. So another thing that we tested also is how the star formation rates are compared considering the same stellar mass range. So here you can see the stellar mass range between 10.6, 11.6 in logarithm, and a comparison between the AGN in blue and then the non-AGN in red. And then in another two stellar mass beams, and we found that even when we consider the same stellar mass range, we are actually dealing with higher star formation rates. So this was published in 2017, as I said, as a part of the MSc of Antoine. And in this paper, we actually suggested that at least for those X-ray detected AGN that do have emission in far infrared, at the redshift that corresponds around 0.6, 0.7, we don't really see the signs of the negative AGN feedback or AGN being responsible for quenching star formation. And we are actually observing enhanced star formation, suggesting that if there is any effect of the AGN on the star formation in galaxies, then we rather observe in these sort of sources positive AGN feedback than the negative one. So these sources might be also, from the observational point of view, good candidates to really study the positive feedback in galaxies that theoretically and through models has been studied quite a lot until now, but through observations less. The next work then was to understand better the morphologies, because we know that if the morphologies of these galaxies are different, it might affect the difference that we are observing in measured star formation rates. So in the second paper, already during the PhD of Antoine, we studied more the morphological properties. So we went through the visual classification using HST data of both AGN and non-AGN galaxies, and then we also measured different parameters and went through different morphological diagrams. So we classified all galaxies into 5 classes, actually 4, plus we had a certain fraction of unclassified galaxies, about 30%. And then we also observed how the different morphological classes are distributed on the main sequence. And we found that a bit stronger fraction of peculiar galaxies being hosted by AGN, about 38% in comparison with the non-AGN, about 20%. Then also lower fraction of spiral AGN galaxies, about 26 in comparison with 46 spirals being related with non-AGN galaxies. And for the AGN, we actually found that on the main sequence, we have different morphological types, and we don't really see early type galaxies being below the main sequence, then later types above or on the main sequence, as we expect for the non-AGN galaxies. So when now we compare for the same stellar mass range, AGN and non-AGN galaxies, and for the same morphological type, we again found independently on the morphology. So here on the left top, you can see for early type galaxies, for spiral on the right, and then below even for peculiar galaxies. So we found again in all three cases higher star formation rates, once again independently on morphological types, suggesting again the same as what we found simply studying the star formation rate, that there might be the positive AGN feedback influencing the star formation activity in these galaxies, and not really the negative one. The next step was to study the stellar populations and ages. Unfortunately, in this case, we didn't have access to the large sample of spectroscopic data. So we used in this case, because once again, we are dealing with high redshift sources. So we used the legacy spectra from VMOS and selected a smaller sample, subsample of the original AGN, non-AGN sample that I mentioned previously. And we went to the spectral fittings using the Starlight code and then the Brusel-Charlotte population synthesis models, including 25 stellar ages, and we assumed solar metallicities. And then we measured for both AGN and AGN, the stellar populations and stellar ages. We only had a spectra for a subsample of about 10% of AGN and AGN. But what we find, even if the sample is smaller, we find that we didn't find very strong differences in terms of the stellar populations and ages, but we do find the consistency in terms of the previous results, so that a bit higher fraction of AGN is hosted by intermediate stellar populations between 10 to 8, 10 to 9 ages, and then a bit older stellar populations we observe in non-AGN galaxies. That still goes in line with, as I said, previous suggestions. Antoine is now working on the paper that we hopefully will submit soon. And currently we are getting the observations from the SALT RSS spectrograph, where we selected last year we got spectra for 4 sources, and then now we are going through the observations of additional 20 sources. So we basically are focusing on analyzing observing the oxygen-free emission line. And what we want to do is to see what are the profiles of this oxygen-free line that has been suggested in previous works to be one of the indicators of the presence of winds and outflows in galaxies. So we basically focus on we selected 24 galaxies, both AGN and AGN, taking into account the same stellar mass and then the same location on the star formation rate stellar mass diagram, so that we can really compare in a very consistent way the profiles of oxygen-free light. And we are currently, as I said, just getting data and going through the data reduction. So with this, I would just like to stress that once we go to the multi-wavelength data, such as far infrared properties of galaxies, that I just went through, we actually see that the image becomes much more complex when only focusing on optical data, and the role of AGN, that AGN might have in galaxy formation, morphological transformation of galaxies, might become more complex as well. So it means that we really need to focus more on multi-wavelength studies. This is another example that I will just briefly mention using sub-millimeter data from the gamma survey, where it's been seen that the area that in optical is less populated by galaxies, called green valley. When we now go to the sub-millimeter data, we actually have what people call the green mountains. So we have the larger population of galaxies in sub-millimeter, of those galaxies that we are actually missing in optical surveys. So just some take-home messages. I think, how much time do I still have? I think I'm running out of time.
Yeah, you are already on. You're already running
exactly. Yeah. So I will just for the take-home messages. Basically, the principal ones are to take care of the selection criteria used in Green Valley. That significant fraction of inside out assembled galaxy candidates may go through the quenching, and then that central star formation might be quenched in help of the AGN before the actually morphological transformation takes place. And then that both when using optical studies, the negative AGN feedback has been suggested, but it's not what we really observe, at least a bit higher redshift when we go to the far infrared data. And before I finish, I would just like to mention very briefly other projects that we are running under the extragalactic group in Ethiopia. All of them are related with the human capacity development and either master PhD projects. So the Tseleke is working on the properties of galaxy and galaxy clusters. Last week, he just defended his PhD, and he's now the very first person to get his PhD in extragalactic astronomy in Ethiopia. Tilahun is working on morphological properties of active galaxies, and currently we are doing very detailed analysis on how AGN may affect the morphological classification of galaxies when we go to the low redshift, high redshift, when dealing with different parameters. With Shimelis, and during his PhD, we are focused on loud radio-quiet quasars and dichotomy. And Paola Marziani, who is in Padova, is helping a lot with this project, and in collaboration with Spain as well. Then with Betty, during her master, we went through the multi-wavelength morphological study of Bassi ultra-hard X-ray AGN, and then with Jeru, through the variability of nearby quasars, we are trying to do the monitoring also using the Entoto Observatory and telescopes in Ethiopia. Asrate, during his MSc, was focused on the accretion rates, and then Daudi is the first MSc student in astronomy in Tanzania. And with him, we went through the better characterization of liners and retired galaxies. So over the last few years, we actually contributed through the research to development of the extragalactic astronomy in different countries in East Africa. And we have now 8 MSc students who defended their MSc. All of them are attached to some of those that are remaining with them. Their MSc are attached to some of the public universities or research centers. 5 of the students are now doing their PhD in Chile, South Africa, Uganda, Tanzania, Ethiopia, Spain. And 3 of them are working in Ethiopia. We have 1 PhD holder and 4 more people to defend their PhD soon. And the very last is just to mention how through the research we can actually contribute to the development, because this is the question that very often we receive. Here you can see on the top the summary of 17 UN Sustainable Development Goals. And here I listed some of the points where directly we do contribute, such as the human capacity building that I just mentioned, And then through the master PhD students and the research that we are going through, we definitely contribute to the very first astronomy and science developments in Ethiopia, East Africa as well. To the international collaborations, because all of the projects involve several countries, especially collaborations with Europe. Then all of our students are already attached to some of the universities in Africa, and once they finish their studies, either master PhD, they go back to their university, continuing to teach hundreds of other students. So we definitely contribute to improving the status of the level of education in the country. And then we also contribute, such as by trying to do the observations through from the Entoto Observatory using South African facilities as well, contribute to the technological development in Africa, but also giving more visibility to the science done in Africa, astronomy done in Africa, and opening the possibility for the future collaborations. And also strong contribution was done because we are really active in terms of the outreach and public awareness and activities. So I can at least mention these 6 sustainable development goals that in one way or another, on a shorter or longer terms, we can really contribute with the research to the, as I said, achieving the sustainable development goals in future. And one example is also the organization of the nuclear activity in galaxies across cosmic time symposium that some of you were here in Ethiopia. It was the very first symposium to be organized in East Africa, and only the third one to be organized in Africa in the last 100 years. And during this symposium, we managed to bring for the very first time international community to go through the students training before, the public talks, the outreach activities with the kids, and then the teachers training as well after the symposium. So we managed to really benefit a much broader community. So I will stop here. Thank you very much for your attention.
Thank you very much, Mirjana. Thank you for this nice talk and also for these last slides. I don't know if someone has any question. We really ran out the time. Okay, I see one hand. Please, Andrea, if you want to unmute yourself and make the question. Okay, I mute, sorry.
Okay, I think I'm muted now, right? Can you hear me?
Yes, you're right.
Okay.
Go ahead.
Nice talk, and congratulations for all the work you're doing for Africa. I just want to know, in one of your last slides, you mentioned the program you have to measure the properties of galaxies in clusters up to redshift 1. So I guess you're going to also to analyze Green Valley galaxies in this project, and which kind of data sets are going to use for this?
Yes, in this project with Celeke, and it was in collaboration with our colleagues from Spain, we actually didn't focus much on the Green Valley. So this project was done under the scope of GLACE, where we've been using the GTC data and the tunable filters data from OSIRIS. So the principle, we have 3 galaxy clusters selected. So the 2 galaxy clusters are with tunable filters data. So we obtained the pseudo spectra using in H-alpha, in oxygen free, and we basically went through the emission line galaxies selection, and then detection, and then classification as well. And then for these emission line galaxies in different clusters, we measured the different properties in terms of we studied morphology, we studied AGN properties, we studied the star formation properties, and then we studied metallicities as well. So it was a bit, it was not really related. I mean, we went through the color stellar mass diagram, measuring how many galaxies we have in the Green Valley and so on, but the sample that has been used is very particular, and as I said, focused on emission line galaxies in general.
Okay, we have another question. Luis Pierre Marie, when you want to make the question. You are on mute.
All right. Yeah. Thank you very much. Yes. First of all, thank you so much for the talk. I mean, very interesting, either scientifically than humanly. I mean, I'm so impressed, and I feel yeah, I used to work in Ethiopia, and actually, this is where I raised my interest in astrophysics, in astronomy, because I was making observation there. And I'm very curious about the Entoto, the observatory in Entoto in Addis in 2015. It was still on the go, and I'm wondering what kind of telescope and what are we expecting to see with this telescope, and yeah, and if it's finished, I guess, because I've seen the picture. So yeah.
Yes, so I didn't know you were in Ethiopia. That's really great to hear. Maybe we can catch up at some moment to exchange more the experiences. So you're welcome to visit us again. So the two telescopes we have at Entoto, two small telescopes, 1 meter telescopes, and they are basically twin telescopes. There is a high resolution spectrograph placed on one of the telescopes, and then a few CCD cameras. So basically, I mean, to build the observatory and to make the observatory fully operational, I think it's always a challenge wherever that you have the astronomical site, but in Ethiopia it was really a challenge, and over the past 5 years we really went through different difficulties, including the lightning that happened a few years ago. And then due to the lightning, many of the components have been burned, and then it took really time to be able again to repair the telescopes. So the telescopes have been repaired again last year. The difficulty is that whatever that we need to do, we cannot find the material on the local market, so everything has to be purchased from abroad, and then it takes a very, very long time. So now the telescopes are operational. We still have some difficulties on one of the domes, but another dome is operational. And unfortunately, when the telescopes were repaired, we entered in the crisis with COVID. So for several months, the work has been stopped, and then that overlapped with the rainy season when we cannot observe in any case. So we basically started with observations in the last few months. And one of the first things that we started was to select some of the nearby quasars, and now we are going through the monitoring of these nearby quasars, trying to work a bit, to see if we can do on the longer term monitoring and study the variability of these quasars. So we are welcoming. Still we have so many things to do regarding the operation of the telescopes. The website is now under the development. So many things are still there to be really done, and there are only few of us being really overloaded with so many assignments, so we don't really have enough capacity. So we do welcome any help in that aspect.
Okay, thank you. And the very last question is, it was in the chat, but I see that also the hand is raised, so I am going to unmute you. Antonuccio, I think if you can speak if you want, when you want.
Just a very short question. Congratulations, first of all. It was a very clear talk. Do you have any hint about a possible temporal evolution of the AGN Green Valley's galaxies?
Yes, I think, as I mentioned, I do think that we really need much more studies, especially including the multi-wavelength data, because obviously there is a sign of both, you know. So theoretically, we know that both positive, negative feedback may affect the star formation properties, activity, and then either the quenching or enhancing of the star formation, and then affect in a different way the evolution of the galaxies. What mainly has been suggested is the negative AGN feedback, and as I said, the positive feedback mainly has been studied through the simulations, theoretically, and in some of the observations as well. So now when we start adding multi-wavelength data, like in infrared, in the work that I mentioned, or in sub-millimeter and radio in general, I think the picture becomes much more complex. So when we really come to the another difficulty that we have, besides, let's say, the detection of the AGN, different samples of the AGN, another difficulty that we have in order to understand the role of AGN in all the morphological transformation is that we really have to have much more complete samples of galaxies in terms of morphological classification. So I think still really a lot of work has to be done in that aspect for the larger samples, and also in comparison, comparing in the consistent way the properties of AGN and AGN. As I said, Green Valley is one of the areas, but then in terms of the whole galaxy population, in order to really understand fully the role in the evolution.
Okay, thank you very much. I think that we close here the seminars. Thank you very much again, Mirjana, for your nice talk and for all you have told us about all your projects. And thank you for all of you that have attended to this meeting. Please remember that you can find in the Laura Bassi Series webpage all the program for the next talks and the information about the next speaker. So thank you very much and good afternoon.
Thanks, everyone.
Thank you, Nancy. Thank you, everybody.
Thank you, Mirjana, very
Bye-bye.
much.
Thank you.
Bye-bye.